So, now we see the molecular forces. Now, surface tension is a molecular formula, is a molecular phenomenon. So, in order to understand it, thus in order to understand its origin, we must know the nature of molecular forces. So, let us see what are the different types of molecular forces. So, molecular forces, the molecular forces are of two types. We will see molecular forces are of two types. Number one is adhesive force, and number two cohesive force. So, adhesive force, cohesive force. So, let us begin with adhesive force. So, adhesive force. So, as the name says, adhesive. So, the general adhesive we use in our common life. Suppose I have to stick two wooden parts, then we use a Fevicol. So, this is an adhesive. So, adhesive is a glue or we general term is adhesive. So, it is a substance which joins two different parts or objects. That means, so adhesive forces are the molecular forces of interaction between dissimilar molecules. So, these are adhesive forces. So, glue binds two different materials by generally these adhesive forces. So, the nature of these forces is very important for glue industry. So, we will study after 2-3 more sessions about capillarity, which is the result of these adhesive forces. So, the phenomenon of capillarity is due to adhesive forces. Now, there is another force, cohesive force. So, cohesive forces. What are cohesive forces? Now, the force of interaction, the molecular force of interaction between same type of molecules is called cohesive force. Cohesive forces. So, if we have suppose water, so inside water there is only water molecules. So, the forces of interaction between the water molecules will be called cohesive forces. So, there are two types of force, adhesive and cohesive forces. So, now let us see what are the different, what is this forces actually, the origin of these forces. So, you see these molecular forces, so adhesive or cohesive, So, any is generally cohesive force. So, no comparison between cohesive which is more and which is less, it depends on the material to material. So, these molecular forces does not obey inverse square law, does not obey inverse square law. In fact, probably they are, probably means we generally guess they are inversely proportional to inversely proportional to the eighth power of the distance. So, you see we call it 1 by r to the power f, that is the force is of the order of 1 by r to the power 8. So, thus this force law makes it a short range force. So, the force decreases rapidly as the eighth power of its distance. So, this makes it a short range force. So, what is a short range force? So, the property of short range is that the force is appreciable, the force is appreciable if the distances between the molecules is inappreciable. So, you see the force is appreciable when the distance is inappreciable, and the force is inappreciable if the distance is appreciable. So, the distance is small, the forces is large. If the distance is large, forces is small. So, this is what happens in a short range force. So, now the range is very limited, not very large. That means, we have a case in which if this is a molecule, then it can influence another molecule over a distance only. That means, suppose I say this is its range of molecular influence. So, what is the range of molecular influence? That means, if I draw a sphere of this radius r equal to the range of molecular influence, that means only those molecules which lie within this sphere will be attracted, and those molecules which are beyond this will not be affected by this molecule. So, we define this as the radius of molecular influence. So, molecular range. What is molecular range? So, the distance to which the maximum distance to which a molecule can influence another molecule is called molecular range. So, now you see the maximum distance to which a molecule can influence another molecule is called molecular range. And so, we have another quantity, another parameter we define, sphere of influence of a molecule. So, it is a sphere drawn with center at the position of a molecule and radius equal to the molecular range. So, this sphere is called sphere of influence. So, now suppose this is my center, this is the main molecule, and I have few other molecules with name A, B, C and D. That means this molecule can only apply force on only C and D, but not A and B, because they lie outside the sphere of this. So, the sphere of influence is this. The molecules lying outside the sphere of influence is not influenced by the molecule at the center. So, the molecules lying outside is not affected. The molecules which lie inside the sphere is only affected. So, thus we see now that there are two types of molecular force, adhesive force and cohesive force. The force does not obey inverse square law, they obey the force law probably as 1 by r to the power 8. Now, a molecule can since this force is a very short range force, so there is a maximum distance up to which this molecule can exert a force on another molecule. So, that is called the range of its molecular force. Now, if I draw a sphere of this range, then all the molecules outside will be free from the influence of this, but all the molecules inside will have a influence of this molecule. So, these are the properties of the molecular forces which gives the bulk property of the surface tension. So, now the origin of the elastic skin of liquids lies in the molecular forces. Thus, surface tension is a molecular phenomenon. So, in order to understand its basic principles, the working of this surface tension, the origin of, we have to see how the molecular forces affect the bulk, the surface and the nearby region. So, what we do? We take some molecules here. So, this is a liquid inside a vessel and this is the free surface of the liquid. Free surface of the liquid. So, now you see here, so we take certain molecules at different positions. So, suppose I have taken a molecule at this position. This is the position of the molecule. This is A. Now, another molecule I have taken which is at here, that is B. So, on the surface I have taken, so let us not take it at on the surface. So, nearby the surface. So, I have taken one molecule nearby this surface. Suppose I have taken this as B. Then another molecule I have taken which is here on the surface. Then I have taken one more molecule here which is here, and then I have taken one more molecule here. So, I have taken few molecules and I name it A, B, C, D and E. So, and now I draw the sphere of influence of A, B, C, D, E molecule. So, you see this is A, I assume A to be a sphere like this. So, let us write this A here. So, this is the sphere of influence, and now you see this is the sphere of influence of B, and you can see the sphere of influence of C also. C is on the surface, so half of the sphere of influence will be above it, and you can see the sphere of influence of D and the sphere of influence of E also. So, I have, so now consider 5 molecules A, B, C, D and E at different positions in a liquid. The sphere of influence of each molecule is shown, in the diagram. So, now let us start one by one with first A, B, C, D and then finally E. So, now let us come to molecule A. Case of molecule A. Now, case of molecule A is the molecule A sphere of influence of molecule A is uniformly populated by similar kind of molecules. So, there is no net resultant of the cohesive forces. So, you see here, we have another molecules from all sides which uniformly populate it. So, you see the sphere is uniformly populated from all directions. Let us magnify this case to understand this. So, this is our molecule at A. So, now you see this molecule here pulls this and this also pulls this. This molecule pulls this molecule and this molecule pulls this. So, this molecule pulls A here, it also pulls. So, it is pulling here, it is pulling here. So, you see you get always force balance. So, there is no net force on the molecules from outside. So, this molecule is applying inward forces and they are also applying the forces pulling A in different directions, and so thus A is surrounded evenly from all directions and enjoys the safety of the bulk, and so there is no favored direction in which the resultant of cohesive forces will go. So there is no net resultant of the cohesive force. Thus, the molecule at A enjoys the safety of the bulk, safety and comfort of the bulk, and has no or least potential energy. So, we will talk about later on that what I mean by potential energy and what potential energy we are talking about. So, I say no potential energy because since there is no net force, I need if I want to move it here and there inside the bulk, I have to do no work. So, I say 0 energy, potential energy, or no change in potential energy. So, this is about A. Now, come to B. Now, come to the case of the molecule at B. Now, the sphere of influence of B is largely inside the liquid and a small portion outside the liquid. So, very small portion outside the liquid. Let us see its magnified view. So, this is the sphere of influence of B, this is the molecule B. So, now you see we have a molecule here, we have a molecule here, we have a molecule here. So, we have the population inside this like this. So, you see all these molecules apply force in this direction and they are also getting force. So, I am mostly bothered about this molecule. Now, outside you see here there is some gas molecules. So, they are few in numbers. So, suppose I say they are few in numbers and I say they are like this. So, they have a very small resultant force like this and like this. So, if they are gas molecules, then they will have a adhesive force. This is adhesive force and these are cohesive forces. So, you see the net force is towards the downward. So, the net force I will say that it is acting downward. So, the resultant of all these forces, this cohesive and two adhesive, is giving a downward force. Now, if there is no air and these are the molecules itself, their density will be less, and so I will not call it adhesive force, but again I will call it a cohesive force. But since it is liquid, so they are densely packed and here they are in gaseous vapor phase, so less. So, this forces upward will be less. So, the sphere of influence, only sphere of influence is this portion is within the liquid. Now, the lower part of the sphere of influence is highly concentrated by similar molecules and the small upper part contains few gas molecules. Thus, the molecule B suffers a net downward force. Now the question is, if it dense, if it suffers net downward force, then why it doesn't go down? It's a basic question, why it doesn't go down? So it does not go down immediately because there is no room. There is no room. That means already there is everywhere packed, everywhere there is packed place. There is no place. That means there is a tendency, but there is no place, so it doesn't. So it has to be there. But there is a tendency to go down. So if there is an opportunity that due to thermal motions any of the molecules has left its place, it will immediately go and fill and then into enjoy its the safety of the bulk, and it will make its sphere of influence buried inside the bulk liquid. Thus, the molecule B has a net tendency to go down the bulk. There is a net resultant of cohesive forces along the downward direction. So it has the tendency to go down. Now let us come to the molecule at C. So molecule C. The molecule C, now the sphere of influence of a molecule C which is on the surface of the liquid is half in the gas phase, and half inside the liquid. Let us not call it by a gas phase. In the air, I won't call it gas phase. In the air and half inside the liquid. So now you see here, this is the sphere of influence of this is the molecule C. This is C. So you see here, this is one molecule, 2, 3, 4, 5, 6, 7, 8, 9 molecules. So it is pulling here. This is the cohesive forces. Outside this molecule, outside the surface, we have a situation where I have few vapor phase, vapors of the same liquid, and I have few air molecules also. So you can see this is going to apply a force similar to this, but this is somewhat different, maybe more or maybe less depending on what is the force of interaction. This is so here this force is very less and this cohesive force is downward, and you can see the cohesive force is here larger than this. So thus as the above, in the above case there is a net downward resultant of the cohesive forces which is the largest in the molecules near the surface. So, we have a molecule B which is near the surface, it is also getting a net force downward, net cohesive force, but this net cohesive force is greatest on the surface of the liquid. So, the surface of the liquid thus, so the molecule at the surface of a liquid feels the greatest force, greatest resultant of cohesive force pulling it down the bulk. So, they have the greatest desire to go inside the bulk, thus they have the greatest desire to move to the bulk. This property of it makes this surface to behave like a stretched membrane. Now, come to the molecule at D. So, molecule D. So, you see the sphere of molecule D, this is D molecule. So, only a small portion is embedded inside the liquid. So, only small force, and rest we have the gas molecules, whether they are similar or dissimilar, and so you see they are more here, and so you see here we exactly can't tell something about D, that whether D, in which direction the resultant of D can be. So, the sphere of influence of D is largely outside the liquid surface, and a small part inside it. So, we have a small part inside it. It is difficult to say whether the net force on the molecule D has a resultant upward or downward. So, it depends on the extent of how much it is inside it and how much it is outside. Thus, if the resultant is downward, the molecule D may come back in the liquid. But if it is upward, then it goes into vapor phase, and thus it comes out of the liquid. So, it can go both ways. So, it can either go up or down. Now, come to molecule at C, a molecule at E. So, the molecule at E, this is the molecule at E, and its sphere of influence is completely occupied by these gas molecules. So, it has a force uniformly placed and so there is no net force as A. This condition of A and E is similar, but the only difference is it is acted upon by cohesive forces and it is acted upon by a adhesive force. So, the molecule, the sphere of influence of E, this is E, is uniformly populated with other gas molecules, and so the net resultant of adhesive. Now, suppose these are vapors, there is no other molecules, then I have to call cohesive. So, net, so I do not call it adhesive nor cohesive, the net force. So, and so the net force, so the net resultant force is 0 and E thus behaves like a gas. So, that means it does not come to the liquid. So, now it is free. It then becomes a free molecule, gas molecule. So, now let us summarize the result and see how these molecular forces give the elastic nature to this surface, free surface. So, we have, now you see this is the free surface, and you see I have a molecule whose sphere of influence is just touching like this, and then so this is the molecule here, this one, and this time slowly this sphere of influence is brought up, means the molecule has been moved to this place. Now, I have moved this molecule to this place somewhat above it, and now it is on the surface. So, you see that here there is no resultant force because the sphere of this is similar to case A, this is similar to case B. So, now I denote this force, that is the net resultant of the cohesive force. So, this force is this much. So, this much force. Now, you see as it goes on, the resultant of the cohesive force becomes somewhat large, and as for this molecule, this force is the largest force. So, when we move a liquid molecule from the bulk towards the surface, we have to do some work against the resultant of their cohesive force, against this force. So, we have to move there, we have to do some work against this force. So, this work done becomes the potential energy of the molecules on the surface. So, thus on the surface, thus the molecules on the surface of a liquid develops develops a intrinsic energy or potential energy, or we call it a surface energy. So, the surface energy is the potential energy of the molecules on the surface. So, from where does this energy comes? This energy comes when we bring the molecules from the bulk to the surface, in which we have to do some work against the resultant of these forces. So, now you see there is a net resultant force on the molecules on the surface. The net resultant force on the molecules of the surface makes them to behave like a stretched membrane. Thus, they are in a state of tension, stretched membrane. Now, this downward force, the downward force acting per unit area of the liquid surface is called internal, intrinsic or cohesive pressure. This is the term, this is the factor which brings A by V square term in van der Waals modified gas equation. Thus, we see that the potential energy of the molecules, so this is not gravitational potential energy, the potential energy of molecules which is the result of work done against cohesive forces, resultant of cohesive forces. Thus, we see that the potential energy of the molecules on the surface of a liquid is the maximum. So, in order to minimize this potential energy, the liquid minimizes its surface area, thus stretching its own skin. Thus, the surface behaves like a stretched membrane and thus wants to minimize its potential energy. This gives rise to a tensile force on the surface called surface tension. Now, it may be defined as the force acting normal to a unit line drawn on the liquid surface which pulls the two parts apart. So, this is how we define the surface tension, and I call this surface tension force as S is equal to that force by length. We will see this. Now, let us see how to define this surface tension force. So, suppose I have this a liquid surface. So, this is our liquid surface. So, what we do? We draw a cut mark here on the surface, imaginary cut part. We can't cut a liquid surface. So, just imagine a line of length dl. So, if I make a cut mark, you just imagine that if we have a stretched surface, suppose I have a bed sheet which is stretched, and if I make a cut and pull it, what will happen? This part will start pulling the liquid along this, and this wall, this side will start pulling along this. As a result, this line will increase. So, how much this surface is stretched, that is the surface tension, can be defined as, suppose this force is dF and this length is dl, and you see this force is always normal to this length. So, the force acting on this by dl. So, we have, so the surface tension as can we the surface tension is defined as the force acting per unit length. So, this force is normal to the unit length. So, this is how we define the surface tension.